Let's talk about something you think you know, something we all learned in school. The speed of light. It's supposed to be the universe's ultimate speed limit, right? A fixed, unchangeable constant. But what if it's not? What if that constant isn't constant at all?
So that's the big question we're going to dig into today. Is the universe's ultimate speed limit really fixed? I mean, answering this could change, well, pretty much everything we think we know about the Big Bang, about the nature of time itself. So let's find out.
Okay, so let's start with the basics, the bedrock idea that we're all familiar with. For more than 100 years, modern physics has been built on this one core principle. The speed of light in a vacuum is constant. And you know what? From where we're standing, that is absolutely true. If you were to measure the speed of light in your room, you'd get the same number every single time. A good way to think about it is like being on a huge, smooth-sailing cruise ship. You don't feel the motion of the ocean. In our little corner of the universe, things are stable, so the speed of light seems constant. And that's the whole foundation of Einstein's theory of relativity. But what if our cruise ship is sailing on an ocean that's constantly changing? To even begin to wrap our heads around that, we need to totally rethink what space is. It's not just an empty void. It's an active, physical medium. So here's the key idea, and it's a big one. Space isn't empty. It's a real physical fabric. And this fabric has a property that's being called elastic resistance. Imagine you have a rubber sheet. If it's all loose and floppy, you can slide your hand across it super easily. But what happens if you stretch that sheet really, really tight? It starts to resist your hand's movement, right? Well, that's the big idea here.
And here's how that plays out over cosmic time. Look at step one. Way back in the early universe, space was less stretched out. That means, as you can see in step two, it had a much lower elastic resistance. Now, let's fast forward. We follow the progression to steps 3 and 4. Today, after billions of years of cosmic expansion, the fabric of space is stretched way tighter, which gives it a much higher elastic resistance. It's a really direct relationship. More stretch equals more resistance. Simple as that.
Okay, so I know what you're probably thinking. How do we square this idea of a changing, stretchy space with the fact that, to us, the speed of light looks totally constant? Well, it all comes down to your point of view. This slide right here, this gets to the heart of it. On the left, you've got our local view. From here, everything looks constant. The resistance is constant, the speed of light is constant, which makes time feel flexible and relative. Exactly what Einstein told us. But then, look at the right, the global view, the big picture. This flips everything on its head. Over the entire history of the cosmos, the elastic resistance changes. That means the speed of light changes. And if the speed of light can change, then maybe time isn't the flexible thing we thought it was. Maybe it's the rigid, unchanging backdrop to a universe that's constantly evolving. Now, this leads us to probably the most mind-bending part of this whole model. If the resistance of space changes and light has to travel through that space, what does that mean for the past? I mean, really think about it. If the elastic resistance of space was lower way back in the early universe, what would that have done to the speed of light traveling through it? And here it is, the staggering conclusion. Because the fabric of space was less resistant, the cosmic speed limit was actually slower back then. You could say light had an easier path, so it just didn't need to travel as fast. This table just lays it all out perfectly. You've got the early universe, less stretched space, lower resistance, and a slower speed of light. And then you have today, more stretched, higher resistance, and a faster speed of light. It's a clear, straightforward progression as the universe has gotten older. So what does this all mean when you put it together? Well, it means we might have to fundamentally rethink one of the most basic constants in all of physics. And here's the key takeaway, straight from the source material. The idea is that the speed of light could have been, and I quote, perhaps significantly lower than it is today. I mean, that's a radical idea because it suggests that the fundamental rules of the universe aren't static. They actually evolve right along with the cosmos itself. And that leaves us with one last, truly fascinating question to just chew on. If something as fundamental as the speed of light isn't fixed, if it can actually evolve with the universe, then what does that say about all the other constants we rely on? What other bedrock principles of reality might just be a little more flexible than we ever imagined?